to be clear, Google will disconnect us after an hour, and so like we can have the Q&A like in Discord.
Okay, yeah, that sounds good.
Okay. Yeah. So hey everyone. Yeah. As I was saying, today I'm going to be talking about Nccl, which is NVIDIA's collective communications library. I'm going to be talking about what it is, why we need it for distributed training, and how it works. We'll dive into an example later, but I wanted to stress that all of this code is available on GitHub. So if anyone's really interested in diving into it, please do that at your own interest. Okay, so let's dive into it. So yes, Nccl is pronounced Nccl. That's how we pronounce it. It's NVIDIA's collective communications library, and it allows for easy point-to-point and collective communication on multiple GPUs. So I've listed some point-to-point operations here that are often done with Nccl. Those are in blue. Some collective operations are in green. And the image here on the lower right is from the Nccl documentation, and it's representing an allgather. So this is just one of the collectives that you could do with Nccl. And what we're seeing is each rank on the left is its own column and has some amount of data that we want to transmit to all the other ranks. So after the allgather step, we're going to end up with each rank having all of the data as shown on the right. And to be explicitly clear, the blue is starting off in the blue data is starting off in rank 0, and it ends up as the first element of all the ranks. The red is the only element of rank 1, and it ends up as the second element of all ranks, and same for the green and the yellow. Another example is scatter and broadcast. These are other collectives or point-to-point operations that you can use in Nccl. This is shown in the top right. And these two operations I highlighted because they seem a little similar, but there's actually a little bit of nuance there. So scatter involves one process sending distinct information to each of the other processes. So this is like a mail carrier delivering specific individual mail to each house. But broadcast involves one process sending the same information to all of the other processes. So this is like a radio station playing the same song, and each radio is tuning in and getting the exact same information. Different algorithms can be used to speed up these collectives based on the number of ranks and other factors, including like topology of your GPUs and how they're interconnected. But we'll look more into this detail later. So one collective that's really interesting and is really important for deep learning is this Allreduce collective. And it's useful for deep learning because we use it to accumulate gradients and reduce them across multiple GPUs. And so we're averaging them across these GPUs. And the goal of the Allreduce is that each GPU gets this reduction from the inputs, and it ends up on all of the individual GPUs. So let's look at this diagram and see what this actually looks like for a 3 GPU case. So on the left, we have, before the Allreduce, we have GPU 0 has ABC, GPU 1 has DEF, GPU 2 has GHI. And after the collective is finished, all of the GPUs are going to end up with the exact same reduction. And the reduction, this is just some operation that we're doing. So it can be like sum or an averaging. And so here we're using the sum as a reduction. And we just need the reduction over all the corresponding elements. So the top row is going to have the sum of the top elements, A plus D plus G, and it's going to have that on each GPU. And same for the middle rows, B, E, H, bottom row, C plus F plus I. And that's essentially the easiest explanation of what Allreduce is. It's gathering all this information and reducing it along some dimension. And we're going to dive deep into how, like, the Nccl, one of the Nccl algorithms that does this later. But why do we need Nccl and this efficient Allreduce collective? Well, as I alluded to, one use case is leveraging using many GPUs in model training, and a popular way to do this is called distributed data parallel, or DDP. So if our model has a very large batch size, it could end up being faster to split the batch across multiple GPUs. So each GPU is computing some subset of the batch, and then we communicate the results between the GPUs later. So how would we actually do that? Well, each GPU is going to get a subset of the batch. So in this diagram, we have our batches x0 and x1, and we're going to split it up into these two components and send them to different GPUs. This data is going to be passed into our model, and importantly, the model is the same on each GPU here. And we run the forward pass of the model, and we get out our y0, or just our output of the model, and our y1 on our respective GPUs. Each GPU also is going to run and notably, y0 and y1 are going to be different because our inputs are different. Even though we have the exact same model, our inputs to the model are different, so our outputs are different. Each GPU is also going to run the backward pass of the model, and it's going to compute local gradients. This is what PyTorch is great at. At this point, each GPU has the same model, but different gradients, and we need the models to be consistent across all the GPUs for every single iteration. So we need each rank to get the average of all the gradients computed on the individual ranks, and accumulate them, average them, and update our individual models on each GPU. That way we have consistent models for every single iteration. And this is just how you'd compute the average gradients of a batch on a single GPU, but now we just need to communicate this data across devices. And this is exactly where Nccl comes in. At this point, we call an Allreduce because each GPU has some gradient, and at the end of the collective, each GPU should have the same average of the gradients. And then after each GPU has these average gradients, they can each independently update their models, knowing that the model is going to be the exact same on each rank for the next iteration because they have the same gradients to update the model.
So there's an interesting question from chat, which is like on GPUs, like floating point. I mean, just generally, floating point numbers are non-associative. So if you like a plus b versus b plus a, that's different. So like, is this the kind of thing people like think about in Nccl explicitly for like to get deterministic runs, or just like any comments? I know it's a more advanced question, but I'd be curious to hear the answer too.
Yeah. So about numerical accuracy for this, I guess the models on each GPU are the same, and the outputs are different. So I wouldn't suspect there's any numerical accuracy concerns beyond like a typical single GPU case. Like there's no extra introduced numerical accuracy issues there. Okay. So let's look at this example more specifically. Like let's look at a toy model to really drive home this point. So our simple DDP model is just going to be setting y equal to some weight that we're going to initialize to be 5 here, and it's going to multiply by some constant, and we're going to multiply it by our input. So then we're going to take our data 0 and 1, and we're going to split it across the two GPUs. We can compute the output of our models here. So y0 is multiplied by 0, so it's going to be 0. Y1 is going to be 7 times 5 times 1, so it's going to be 35. And then the gradients of our outputs with respect to the weights is easy to compute as well. It's just 7 times x. And so we can easily compute the local gradients, which are just 0 on GPU 0 and 7 on GPU 1. Then the Allreduce is going to average these gradients across the two GPUs, and we're going to get 3.5 on both. And then we can use these average gradients to update the models on so that both GPUs have the same model for the next iteration. And we can look at what one of these examples looks like. I'm going to start by just running this code here. Well, I guess to start, this is using Lightning AI. We have 4 Tesla T4 GPUs, just running an NVIDIA SMI. And we have this simple DDP model that we're going to take a look at. And I'm going to start just by running it so we can look at the code and what's printed out at the exact same time. We use torch run, which is just launching the code on multiple processes. And so we're specifying 2 processes here. And so we're only going to use 2 GPUs. And we'll end up seeing so we're understanding it. We should see it's going to run this. It's going to launch the code for on each process. So we should see running here twice. So let's just start by launching this. And we see that it's running. Okay. So all torch run is doing is just launching it on multiple processes. Okay, so let's actually look through this code and see what it's actually doing. First, we're just importing a bunch of torch things. We're torch distributed, torch profiler, and our wrapper for DDP. We'll go into what these things are in a second. We're going to define our toy model, which we saw before. Just takes a single parameter. We initialize it to 5, and it's going to multiply W times 7 times X there. And so when we run this demo, we start by whenever we run this distributed code, we use torch distributed, and it is kind of like the front end that uses Nccl on the back end and calls Nccl to do all of the operations that we need, like this Allreduce. So this distributed init process group is setting up all the processes and saying, okay, which processes are involved in these collective communications, and that's a general idea. And then by passing in Nccl, we're telling it, okay, use Nccl as the backend and to run all these collectives. So it does some Nccl initialization stuff here as well. And by running this, we can now call dis.getRank, and that's just saying for each process, we have a unique ID for it. So we're going to start running basic DDP example on rank, and we see that rank 0 or rank 1 prints on rank 1, rank 0 prints on rank 0. So pretty self-explanatory there. Then what we're going to do is we're going to take our toy model and put it on different GPUs. We're going to wrap our model in this DDP wrapper, and that's going to just handle all of the gradient reduction for us. We'll dive in deeper to what it's doing, but this is just a high level of what it's of what this wrapper is doing. We can use a profile, which is just a way to. I think there was a profiler talk last week, but this is just a way to see what is running on CPU and GPU, and generate a nice trace with it. And we'll look at one of those in a second. Then as we saw, we're going to get our just pass in some input data, 0 for rank 0, 1 for rank 1, and we're going to pass it into our model. And we see, just as expected, printing out the forward of Y0. So rank 0 forward, we get 0 here. 5 times 7 times 0, makes sense. For rank 1, we get 35, 5 times 7 times 1. Okay, so we're computing. What we're seeing now is we're seeing that we're executing the exact same model on different GPUs and getting different outputs because we gave in different inputs. Then we can compute local gradients as well. We know that it's 7 times X, so we know it should be 0 and 7 on the respective GPUs. And y.backward is going to take all of our is going to actually run the autograd. So it's going to generate the gradients for this. So it's going to generate the 7x essentially, the 7 and the 0, and then it's going to call the Allreduce, and it's going to put the reductions. So the average of 0 and 7 is 3.5, and it's going to put them in the .grad for the parameters. And we see that if we print this out, we get the reduced grad for both as 3.5. And I don't have any optimizer here, but we would then use this gradient to update the model, and then we'd have the same model on different GPUs. So switching over to
so then actually I have a question here. So when you're calling like Y backwards here, like what is happening exactly? Is it basically you're running a backwards pass per GPU, and then when you're calling dot item is when the synchronization is happening, or is the synchronization happening at the per backwards layer?
it's happening at the per backwards layer. So it runs the entire backward, computes the local gradients, calls the Allreduce, and updates it in the backward. I'll go into we'll look at a trace in a second, and that should give kind of a better idea of what's going on too.
Thank you.
So a slightly more realistic example, still a toy model, but something with actual like map moles. We'll look at that real quick. So this example is very similar to before, but now we just have 3 linear layers, and we have like a linear layer, then a ReLU, linear, ReLU, linear. And so we'll actually need some matrix multiplications here. And we're also going to, much of this code is exactly the same. The only main differences are we have an optimizer now, so we're actually going to update the model, and we have a loss function, a more realistic loss function here. If we run this code, just for sake of it, we're not printing out anything interesting, but what we can do is we can use profiler.export Chrome trace to generate these traces. This is just telling us what's happening on the CPU and GPU, and it's going to give us this JSON file, which we can open with Chrome tracing. And if we like look at this trace, we can kind of get some interesting information here. First of all, this is just rank 0, so this is just one of the GPUs that we're looking at the trace for. So that's kind of important. And we see CPU operations on top here. This is forward operations. This is backward operations. And then we have GPU operations at the bottom. And we have these 2 different streams here, which we'll kind of talk about in a second. But let's actually look at one of these 4. And so we run this for 10 iterations, and we get 10 iterations here. So like we can look at one of these forward passes. Each one of these is a forward pass, or is an entire iteration. So forward, backward, optimizer, step, everything. Let's zoom into just one of these iterations. So this is again happening on GPU here, and we can see some memory operations, getting the inputs to the GPUs, and then we have this gem kernel. So this is a matrix multiplication. So this is the first linear layer, and then it's followed by a ReLU. So you can kind of see, okay, there's clamping here, which is what ReLU is doing, followed by another matrix multiplication, followed by another ReLU, followed by another matrix. So this is our forward pass right here, and we can measure how long it takes. We can do a bunch of things. So this is a really useful tool for figuring out what's going on on our GPUs. We have some loss computations here, and then we start our backward pass. And one thing we can do to see where these GPU kernels are being launched is we can click on these individual flows. So we can scroll into the what CPU operation is calling the GPU kernels and launching these, and we can see that it's a backward pass operation that's launching the these gems in the backward pass. Okay, so there's a lot going on here, but after this, we can look at these individual gem. We see individual kernels in the backward operation, computing gradients. We also see these Allreduces that are generated, even though we don't explicitly call them in our Python code. Eventually, we have some optimizer update steps later, but that's essentially what we can get from this kernel. So I think the interesting things are, how is this Allreduce actually being called? Because we don't explicitly call it in our Python code. Another interesting question is, why is it in a different stream? Like, what does this mean? Why is it overlapped here? And so So that's kind of what we want to uncover on this next slide. So to start off, let's talk about this other line that's representing a different CUDA stream, and I have part of it, a screenshot of this trace copied down here. So this other line is a CUDA stream, and a CUDA stream is a sequence of operations that execute in issue order on the GPU. So what that means is that operations that are in the same stream and are launched have to execute in that launch order. But operations in different streams can run concurrently. So on the GPU, this matrix multiplication is actually running at the same time as this Allreduce operation. So why do we actually want the Allreduces to happen concurrently with these backward operations? Well, the Allreduce is just averaging gradients, but if we think about what is actually going on in the backward pass, we notice that it starts by computing the gradients for, let's say, the last layer, and then it slowly works its way back to front to compute the gradients along the way from the back layers to the first layer. And what we could do is we could just wait for the backward pass to finish, and then we have all of our local gradients, and then we just average all of the layered gradients at once and call an Allreduce, and we just call an Allreduce at the end. But it's actually faster to start the collective for the last layer when those gradients are ready. It doesn't make sense to wait for this entire time and then spend time reducing all of the gradients at the same time when you can get started by when the last layer gradients are ready. So it's kind of like a pipelining thing. And this way we're actually overlapping the computation and communication so that by the end of the backward pass operations, we only have to reduce some small subset of the gradients associated with like the first few layers. And I'm simplifying a bit here. There's actually what's actually going on in DDP is there's like individual buckets for gradients, but this is just the main idea of why we can overlap the matrix multiplications with the Allreduce operations. Also note that we can make the Allreduce operation on one stream wait until the gradients are computed on a different stream. So like that's why there's some we're not launching immediately. We schedule it at some point and then we have to wait for these gradients to actually be ready. So we're not transmitting just garbage information. And as for how the Allreduce is actually being called, that is being handled by DDP, and that's handling the Allreduce call and all of the overlapping as well in PyTorch under the hood. It uses PyTorch DDP is what it's actually doing is it's using autograd hooks to trigger these gradient sinks and compute the mean of the gradients along all of these processes. So it we are computing the gradients, it launches these Allreduces automatically, or not launches, but it says that it's ready to compute the mean of the gradients at this point. And then once this is done, the average gradients are written to the grad field so that the parameter of the grad parameter on all GPUs has the exact same value. I should mention that Nccl is not the only way to do this. There's other these collective operations are not exclusive to GPUs. You can also run it on CPUs. You can run it on a bunch of things. So you can also use something like MPI to communicate all these gradient values. And for anyone interested in exactly how this Nccl API is called, you can look at the process group ncl.cpp on GitHub. So that's all open source as well. So it's really nice that we can kind of see there's nothing really behind. We can see exactly everything that's happening from the PyTorch level to the Nccl level, and that's really helpful. Okay, so this is kind of the end of the PyTorch side of the talk and how it's being used, and kind of diving more into Nccl now. we've seen what PyTorch is doing, how it's using Allreduce for model training, and now we want to move into what Ncl is actually doing when it is being called. So here's a look at Ncl's Allreduce API that PyTorch is calling. It takes in a send buffer of size count. So this is all information that the collective needs. It reduces it using the operation, and it copies the result to a receive buffer. The function also takes in some other things, including data type and a cuda stream, which we just kind of touched on. But it also takes in this interesting thing, a communication primitive called a communicator object. And this communicator object is used to refer to the collection of GPUs that are working together. So it's saying, it's very similar to the init process group from before. It's saying, okay, which GPUs are we using in these like Allreduce operations? So yeah, these communicator objects are just how these processes know what other processes it should communicate with. There's a couple of ways to initialize this depending on like the number of CPUs and GPUs that you're using. If each GPU has an associated CPU process, a unique ID is generated by the root process on the host side. So there's a single process, that root process, that generates this unique ID, and then it broadcasts this ID to all of the other processes using something like MPI. So this is all happening on the host code, all happening on the host. Then each process is going to initialize this communicator object using the exact same ID that it just was broadcast to, but it's going to use the ranks that it is associated, the MPI rank that it was associated with. So it uses a existing process ID or process number already to initialize this communicator object. So then when we actually are calling the Allreduce with this, we pass in this communicator object, and all of the processes know like who they're working with. Like we're working with these different GPUs to do the Allreduce here. Moving down to the second part, you can also initialize these GPUs on a single CPU process. The same idea is followed, but you don't have to broadcast this unique ID because you have all the information in this process. So you just loop through the initialization for each of these ranks. This is just a Ncl wrapper on the right that does this for you. It just again, it creates the unique ID, sets the device, and then calls this init for each of these devices.
Then may I ask a question to this multi-process thing in general? What happens when one process discovers it has ran into an error and needs to, for example, shut down? Is there a way to somehow gracefully shut down the whole group of processes, or to signal it to, I don't know, like the rank 0 or what's like? Is there a recipe to follow in these cases, or is it just normally it should always work?
No, that's a great question. And my understanding that it is an active problem that we are running into, especially as we use more and more GPUs, when there's more likely of a chance that one of them will fail. And there's a lot of ways to track this. One thing that PyTorch does is it has this like heartbeat timer to make sure that, or heartbeat timeout that is always checking to make sure that everything is running. So there's ways to do it, but some things are scaling better than others. So long story short is it seems to be an open area of figuring out how we're doing this.
Okay. So I have a comment on this and then a question. Like, so imagine you have n GPUs and one of them dies. The sort of main way this is like resolved today is like, I think what Daniel was alluding to, which is like a heartbeat. You sort of say, hey, there's a GPU that's down. You stop the world, and you basically wait until a new GPU gets like spun up, and you keep going. And as far as I know, this is sort of like the main way people do like elasticity and training. The reason why people don't continue training a job with fewer GPUs in case one failed is because this would change the numerics of your program. Like basically your global batch size reduces, and effectively you can't reproduce like the same loss curves. And I think that's why in practice people don't do it. But I think, you know, with hundreds of thousands of GPUs, I think waiting is not acceptable, and maybe losses of accuracy are more okay. We'll see.
Yeah, I think that's a great comment. Yeah, I think that makes a lot of sense.
I guess my unrelated question was, so you mentioned this one GPU per CPU process versus multiple GPUs on one CPU process. Like what are the trade-offs for each? Like when would you choose to do one versus the other?
I think it's largely dependent on your PyTorch will generate one GPU per CPU process, and it uses that for the entire time. I think the trade-off is being able to have these individual threads running and kind of tracking all of these operations, launching them all at the same time. So I think that's why PyTorch is using one GPU per CPU process.
Got it. Thank you.
Okay, so we'll dive. I think I'm a little behind on time, or maybe it's okay. So we'll dive into one example that is using. Let's look at one of these examples with just a single CPU process, just to kind of decouple what PyTorch is doing, but give us an idea of what PyTorch is doing, but also see how it is like launching running this code on the host side. So get an idea of how we're actually launching these kernels, setting up the buffers and everything. We're going to look at a single process example, and this is just taken from Nccel's documentation. They have an example of running an Allreduce in there. And here there's a single host process that is managing multiple GPUs. Right now, the start of it is just importing libraries and defining some like error checking macros, and again, all happening on the host. Then it allocates some communicator objects. Each object refers to like one of our fixed GPUs. And they have to be. These objects have to be initialized, but this is going to come. Come a bit later. This example uses 4 devices and is storing 32 million floats on each device for a total of like half a gigabyte over all 4 devices. Next, the send and receive buffers are just allocated on the host side. And that's just going to be used to keep track of the associated buffers on each device. We also allocate a cuda stream here. That's what we saw before, but we're allocating one for each of the devices, and then we allocate the send buffers on each device, the receive buffers on each device. And we set them all the values of the send buffer to 1, all the values of the receive buffer to 0. So this is just their example of running a single process and kind of stepping through it. Again, all happening on the host so far. Then we call this kind of wrapper that I was talking about before, this initialization wrapper, since we're using single process. These communicator objects are all initialized, and that's going to be passed to the collective calls, so they know who to talk to during their collectives. And then they call the Allreduce. And it's called for each device and with each of their respective send buffers, receive buffers, communicator objects, streams, etc. And also specified here is the size of the send buffer, the data type, the operation that it's doing, and so nickel sum, and the communicator object and the stream. So this is just the API that we saw a second ago. And we're going to look more closely at this, like what's happening on the GPU side for this Allreduce kernel in a second. But I want to stress here that when we're launching these kernels from so when we're launching these like Nickel kernels, from the device side perspective, there's nothing special about it being a Nickel kernel. It's just a regular CUDA kernel from the device side, and it's just doing memory copies, and it has to contend for the same resources as any other kernel. It has to contend with like the memory bandwidth, the registers, SMs, everything just like every other kernel. And then finally, there's a synchronization waiting for all of the Nickel operations to finish. Just cleaning up the rest of this example. The memory on the GPU is freed. They don't really, they forget to free the memory in the host, but then you have to destroy these communicator objects as well. And so this is all of the host code that runs this single example. And to compare that to like this other case with 1 GPU per CPU process, it's very much the same thing. But now we have the main interesting differences is we have to broadcast this unique ID and at the start, and we do the initialization a single time on each process, and then we only call a single Nickel Allreduce because it's each individual process is calling this exact same code. And so this is again host code, but it's running on each process it's running in parallel on each process. So now diving into like what's actually being called when we call this Nickel Allreduce. The actual Allreduce algorithm can be implemented in a few different ways, and Nickel is smart about this. It estimates how long each of these methods are going to take based on the network topology, and then it picks the fastest. So one of these methods, one of these algorithms, is using a ring structure and essentially performs a reduce scatter, which is represented here, and an all gather represented here. So let's briefly look at how we get an all reduce from these two operations. We start with all of our data here on each of our individual ranks, and we call a reduce scatter, and that's going to give individual reductions, but only existing on individual ranks. Then calling it all gather is just going to take all these ranks or all these individual reductions, and it's going to put them on each individual rank. So now we start with all the data here on individual ranks, and we end up with the reductions on all of the ranks. So that's how a reduce scatter plus all gather is going to give us this all reduce operation. So in the actual Nickel code, it looks like it's a bit dense, but we can look through it at a kind of a high level. So this is just a single algorithm for Allreduce. So it's the ring algorithm, and the code that we're looking at now is executed on every single GPU in parallel. It's going to start by doing a lot of familiar CUDA things like block ID, thread ID. It's going to initialize some of the like the structure of the collective. So it's going to create the ring, and it's going to create the primitives that are actually doing the send and the receives. We'll talk about that in a second. And the algorithm is going to work by on chunks of the send buffer at a single time. So this first part of the code is just taking our individual send buffer, and it's just grabbing some chunk of that on each GPU. It's grabbing the first, we'll just say the first chunk of each of the send buffers on each GPU. So that's what's going on here. Then after the step 0 comment, it's going to push the data to the next GPU. So all it's going to do is just going to send this chunk to the next GPU that it needs to. This prims.send call, it's how they actually send the data to each GPUs, to the other GPUs. There's a bunch of different ways that they can do this. It's a bit outside of the scope of this talk, but there are like direct connections between GPUs, like super fast connections, like called NVLink. These typically exist between GPUs on a single node. There's also ways to put data on other GPUs directly, including InfiniBand, Rocky. So if interested about any of these things, I definitely suggest taking a look at. I have a guide later on the last slide about a source that is useful to get into this space as well. So this prim.send is just using these connections to send the data to the next GPU, and it determines which of these connections to use during the initialization of Nccl. But back to the Allreduce algorithm, each GPU is sending a chunk of data from the send buffer to the next GPU. So back to our simple 3 GPU A, B, C, D, E, F, G, H, I example. When there are when we have these 3 GPUs, the algorithm is just taking a chunk of each GPU, and it's sending it to the next GPU. So A is sending to GPU 1, etc. But they're all operating on a chunk, and they're offset in order to do this in a fast, optimal way. It then goes around in a ring where it receives chunks from the previous GPU, reduces it to receives chunks from the previous GPU, reduces it. So this is the reduce scatter aspect of it, and then it pushes the reduction to the next GPU. So receive, reduce, send. So GPU 1 is receiving D from GPU 0. It reduces it, so it just does the sum, A plus D, and then it's going to send it to the next GPU. So now we get A plus D sent to GPU 2. It's going to keep going around in a ring over and over and over until it makes its way around one time. Then it's going to save this final result, this reduction, to the output buffer, to essentially what the place in memory where we want the reduction to be after we get this result. And then now we kind of have a problem. We've done the reduce scatter part, so we have the reduction on each individual GPU. We have A plus D plus G on GPU 2, BEH on GPU 0, CFI on GPU 1, but we still need to make sure that all of the ranks have the exact same reductions. So we finish the reduction, we do this copy to the output buffer, and then we send it on its way to the next GPU. So A plus D plus G is now being sent to GPU 0. And on GPU 0 and all of these GPUs, it's just copying it, or it's receiving it, copying it, and sending it on its way. So it receives it, copies it, sends it on its way. Receives it, copies it, sends it on its way. So in this way, we're taking the individual components of the reduce scatter and then doing an all gather by sending the data in a ring around to get to all the GPUs. So that's kind of the main topics I wanted to cover. Hopefully this has been a decent top-down look from how PyTorch leverages Nccl to do collective communication for its large-scale training. Thank you for coming and listening. There is a lot more to explore in this space, including there's other Allreduce algorithms. So you can also do this with this Allreduce as a tree. It might be more efficient to compute the reduction where you take each GPU as an individual leaf, and you send the chunks to the parent nodes, where it receives it. The parent nodes receive it, does the reduction, and then passes it on to their parents, which receive it, reduce, pass it on to the parents, all the way up to the top, and then it does the final reduction, and then it broadcasts all the way back down to the bottom. So there's a bunch of different ways to do this, and again, Nickel is going to pick the fastest way to do it. Another aspect is a really interesting aspect is this network topology and the connections between the ranks. And I found this introduction to InfiniBand for end users to be really helpful to understand InfiniBand and Rocky. And then finally, there are also different ways the primitives are implemented, which give Nickel a lot of flexibility in maximizing the network bandwidth. So that's kind of a whole other can of worms that you can look into. So there's a lot going on here. Hopefully this has been a nice surface level and then kind of deeper dive into one of those algorithms for Allreduce. Thank you, and I think that's all I got.
Awesome. Thank you so much, Dan. Really appreciate the talk. Folks, please shower Dan with a bunch of emojis. We are gonna get kicked out of this room in about 12 minutes or so. So we'll move to the Discord. Let's just move to the Discord reading group channel now, and we'll see everyone there, and you can just ask the Dan question.
Translate to Nickel.
Yeah, they do have global and local rank. I think just in general, you can have a single node might have 8 GPUs. So you can have and this node might be connected by kind of what I was alluding to before, faster connections like NVLink, which you can transmit data between the 2 GPUs faster. So that's your local rank. You have 8 GPUs there. You have 0 to 7. But then you also can communicate across different nodes. So if you have another node that has another 0 to 7, then that's how you get your global rank, 0 to 15, say, and that's all set up during initialization.
All right. Okay.
Okay, I invited Byron up, but he left. It seems I don't know what's going on his end. So I guess I'll ask a question. So this is more about micro benchmarking. I think you mentioned sort of one interesting thing, Dan, which is you might think about, hey, let me increase my batch size up to a certain point where it might make more sense for me to now do something like DDP. So I'm sort of curious, have you sort of developed any workflows for back of the envelope math when you can sort of estimate when DDP might make sense versus staying on single node and making the models smaller, for instance?
Yeah, that's a really good question. I think I think there's different regions of size that like you were saying, that it would be faster to run a bunch of matrix multiplications and then communicate the data versus actually running it all on a single GPU. I think the main motivation for people to run DDP at the moment is because you run out of memory on a single GPU at some point. So these very, very large models you can't fit on a single GPU. So for DDP, you have to fit your entire model on a single GPU. But the motivation for there's different ways you can scale to more GPUs, including this thing called FSDP, which is another data parallel method of training. But what it does is it splits up the model into different chunks, and you are able to fit a model larger than you would be able to on a single GPU across multiple GPUs and run the entire thing. So it still seems very you got to play with it to figure out when you can get the performance out of it. I've talked to some people about like when you can use like a single level of parallelism or multiple levels of parallelism, and there seems to be some general guidelines about, usually depending on like number of parameters of your model. Once you get it above a certain level, you can actually see performance gain. But my understanding is there's a lot of playing around with it. And then one other thing I'll say about just because you mentioned micro benchmarking, there's another open source library called Nccl tests that you can compile Nccl against, and you can run all of these operations across however many GPUs you have and get the bus bandwidth of all of the operations just to see how fast these each thing is going. And it goes through the entire initialization to make sure that it's using the best network topology and that it can find. And so that's another thing that's worth noting.
That's really interesting. Like that feels like the kind of thing that like Stas Beckman would have to sort of like just quickly micro benchmark a distributed setup. Anyway, like thank you so much. Like, and Byron, I do want to give him a chance because I think I saw him ask written questions or so.
Thank
So
you.
please
Can you
go
hear
ahead.
me?
Yeah.
Yeah, I have two questions. One is about the profiling. So, are you aware of any profiling tool in the open source that can do distributed training profiling? So I can see, for example, multi GPU on one view, because usually what I use is just do on one rank.
Yeah, I'm not aware of an open source one that does that. I also usually open up multiple traces to kind of cross compare. You can do some analysis. I've written some analysis tools that essentially. So what? Why? First of all, why would you want to do this? Is if you have some operations like rank 0 that's doing some like data pre-processing or something, it might be that you run these operations, and then on your other ranks, you're not doing these intensive operations. So you launch a Nccl kernel on the other ranks, and it looks like it's a very, very long kernel, but it's actually just waiting for a little bit, waiting for some time while rank 0 is finishing off all the pre-processing, and then waiting for rank 0 to join the collective.
Makes sense. And
So
do you
you can-
usually use? Oh, go ahead.
Well, so one thing you can do is you can take the look at. I have some analysis tool that takes these individual traces and then takes like a minimum across the collectives, and you can use that to kind of get a data transfer time, just so you're not like you don't see the Nccl like kernel waiting for a super long amount of time. So that could be useful, but it's just Python parsing the JSON files.
So within that line, actually, there is an open source tool. I forget if it's in PyTorch or in the Facebook research org, but it was called Holistic Trace Analysis, and I think it was like done by like one of Dan's like former peers as well. But it gives you sort of like, it sort of does this sort of data collection. It'll give you like, for example, like an overlap percentage for your workflow. So it might not be like a single visualization, but it'll give you the numbers that you need to make smaller. And I found that to be very helpful for folks.
Oh yeah, that's very useful. I didn't know that was open source. So yeah, that's also very useful.
And do you usually use Perfecto or Chrome Trace or TensorBoard?
I've been usually using Chrome tracing.
I see.
I think it's just a preference thing.
I see, because every time I use Perfecto, it's easy to crash. It's usually crashing.
I've had a similar experience.
Yeah, and another question is that you mentioned there are two modes of collect. So one is for one GPU and one CPU. The other is multi GPU, one CPU. And which one does FSDP and DDP use in PyTorch?
I think they use single GPU or single process. So one GPU per process.
I see. Okay, thank you.
So any other questions?
All right, I think I just see Andreas typing. So, like, considering things are, I see two people now posting, Attack or Die and Bruno. and Andreas, like a bunch of people. We'll just give him a second.
Okay.
Come on,
So
folks.
in general, if somebody wants to ask a question in person, also please just request to speak on this stage.
Indeed, that might be faster.
One thread could be 8-bit and the other could be 32-bit. So we're regarding so if we don't broadcast, maybe this is the question, and so all the tensors on the individual devices, they have probably to be the same, right? So you can't just the operations in general have to be the same order and so on. Obviously, otherwise it would just deadlock probably.
Yeah, I think it would. I'm not sure if it would hang or throw an error at that point, but it would probably throw an error. Yeah.
Actually, then I have a question. Like, I've heard this meme that like Nickel deadlocks a lot. Like what is that about? Like, could you sort of unpack like why that happens in particular for Nickel?
I think. Well, one thing is writing distributed code can be like tricky. So I can talk about like one example I've seen where someone was had inputs on different devices, and this is at the PyTorch level. They had their inputs on different devices, and then they all gather or maybe an all to all or something, some operation to transmit the data between, and then they compute some loss on their individual GPUs. But then they also wanted to compute individual gradients in the same way. But so they call the forward pass. They implement some model that has a forward pass that includes this all to all operation. Again, in the PyTorch level, you can call it through this C10D distributed class. And when they wrote the backward in this case, they wrote it in such a way that each individual GPU or each individual process was calling the inverse of the operation in such a way that it was not joining each other. So they were joining different collectives, and so they were both waiting on each other to join the others collective, and then it was just hanging there forever. So I think it's in general it can be really tricky to like write distributed code. But on the other hand, when there is a lot when you get into these very large like jobs, and there's some operations on some ranks that are like doing some pre-processing or other things, and maybe it's taking longer for whatever reason to do the pre-processing. Well, the other ranks are waiting, and they're waiting for the rank 0 to join these collectives. And in the meantime, they have this heartbeat timer, right? Just going and waiting, and if it gets to a point where it hits that heartbeat timeout, then you get a Nccl error, even though it's not super related to Nccl in this case, right? It's that the rank 0 was taking more time to do the data pre-processing than there's a lot of cases where, okay, we look at the trace of we look at the logs of the jobs, and we see, okay, Nccl error here, and okay, so that must be Nccl doing something wrong, or it could be kind of like misleading and something else is causing the issue.
Interesting. Well, okay. I think maybe this is like a natural place to call it. Dan, thank you so much for coming in and talking to us about your experience like with Nccl. Please, folks, just shower Dan with like a bunch of emojis, so we can encourage him to come give us a talk again. Thank you so much, Dan.
Yeah, thank you for giving me the platform to talk. Appreciate it.
So next week we're going to be having Kapil Sharma, also from Meta, who's going to come talk to us about his experience optimizing some kernels. So it's going to be a very profiling heavy talk, I think similar to Taylor's talk from last week. So yeah, thanks again, Dan. Really appreciate you coming in, and see everyone next week.